Good morning. I'm going to show this video because since I didn't succeed with the blue button this morning, so I'm recording this video for the lecture that I was planning to present. So we are on chapter 13 on chemical equilibrium, and these are the list of topics that we're going to cover: the conditions for equilibrium, and looking at equilibrium constant, and then we'll look at some of the different types of equilibrium and application. So let's start with a chemical reaction. If you look at a chemical reaction in the way that we have been discussing and learning, we know that the reaction has got the reactants and products with an arrow indicating the direction of the reaction. So this arrow here indicates that it's moving, the reactants are moving to form the products. The question we have is, to what extent are the products going to be all be left at the end of the reaction? Or is it going to be products with some of the reactants? So these are the questions that are going to be answered here when we deal with equilibrium. And it is important to note that we also will carry the coefficients, the mole ratios, when we are dealing with any reaction. Now, we will specifically focus on this arrow here, because what we'll see here, that instead of just one direction, it's going to be the forward and also the reverse. So definition of equilibrium is a state where concentration of all reactants and products remain constant with time. So time is not really a critical factor. In other words, it's not factored into the equilibrium relationship. So in terms of an equilibrium, when it is formed, you may see that some have more of the products, and others you may have more of the reactants in the state of equilibrium. Or even in some situations you have equal proportion of products and reactants. Now, what we're going to look at in terms of equilibrium is this sort of reactions. For example, if you have CO, carbon monoxide gas, reacting with water, it forms hydrogen and carbon dioxide, hydrogen gas and carbon dioxide. So this reaction here, in terms of the stoichiometry, you can see that the equation is balanced. There is one carbon, and you see there's two oxygen and two oxygen and two hydrogen. So we have the balanced equation. So the mole ratio here is all 1 to 1. Now, when you start this reaction, for example, it may begin like you have 1 mole of this and 1 mole of this to begin to mix together. And at the beginning, there should be 0 of hydrogen and carbon dioxide. Now, suppose that you leave the reaction and it goes for some time, and it comes to a stop. You would expect this relationship. At the end, you have X amount that has reacted from CO and X amount has reacted from H2O, and therefore, using the stoichiometric, that means it is the same amount, X, of hydrogen formed and carbon dioxide, X, is also formed. So here, when we come to this end part of the reaction, this is where we are talking about. This is the state where it reaches equilibrium. The reaction doesn't move forward or doesn't move backward in a major way in order to cause change in the system. Now, if you look at this plot, that shows the trend of the reactants and products. So you'll see here the two reactants, carbon monoxide and water. Over time, they decrease in the concentration. Notice that this is the concentration versus time. So the concentration of the reactants decreases. On the other hand, the concentration of the products, carbon dioxide and hydrogen, starts from 0 and increases. But I'd like you to note on this side here, towards the far end on the right, you will see now that there is no more change in the quantity at equilibrium for both the reactant and the products. So over time, they remain virtually constant. So this is the area or the region we are talking about. That's when the system or the reaction is at equilibrium. Now, before it reaches equilibrium, we should note the following, that the reactant, as it progresses to equilibrium, this is the rate that is demonstrated. So I'm using a different plot here. This is the reaction rate, and that is the time. So you'll see here that the rate in which the reactants are changing to form the products is shown by this curve. It shows a much faster rate compared to this one has a slower rate. This is the reverse rate. In other words, the rate in which the products changes to form reactants. So you look at the two rates, they are entirely different. And we learned that from kinetics because the slope of this curve here, or generally it should already be indicated here. So you can see that the steepest slope here shows a much greater rate compared to this one here. But when it reaches equilibrium, note this, the rate is the same. So in other words, the concentration remains constant, as we've seen in the previous slide, and the rate is the same. That is, we can say the rate of the forward reaction is equal to the rate of the reverse reaction. So these are some of the factors that determines the position of equilibrium. I'm going to define the position of equilibrium a little bit more. These are the initial concentrations of the reactants and the products, and relative energies of the reactants and products. Now we'll notice that the form of energy is going to be covered in a lot more detail later when we deal with some of the concepts of entropy and free energy, relative degree of organization of reactants and products. So those are the three that determines the position of equilibrium in a reaction. Now let's look at the definition of equilibrium in terms of a mathematical expression. We define that in terms of an equilibrium constant. So we look at the law of mass action. Law of mass action really is that the quantities you started off with is the same as what you get at the end, as we know from the very early on in general chemistry. So ignore this straight sign here. This is typo error, and it should be the double-headed arrow here. It should be going forward and back. And I'll try and see if I can use some of these tools to show what I mean by this. Let me try this. Pen. Okay. So this should be arrow pointing forward, and also an arrow pointing backwards. I'm going to try and put it just below here. So that double-headed arrow is its equilibrium symbol or sign. All right. So now let's continue. So in a reaction A and B with the mole quantities to give you C and D, A, B, C, and D are chemical species or compounds, and those small letters, as you know, are the coefficients, which are the mole ratios. So in the law of mass action, represented by the following, expresses the equilibrium constant as K, capitalized K, and K is equal to the concentration of products raised to its coefficient, that'll be the power, and multiply by the concentration of the other product. So in other words, product concentration raised to the coefficient, and divided by the concentration of the reactants raised to their power. So these are product terms. Products meaning multiplication term, that is. So products over reactants raised to their coefficient. So the square parenthesis, you know that it represents the concentration, and the K value is term what we call the equilibrium constant. Sometimes we'll see this term here, K, represented as K with either EQ or K as subscript C. This pretty much means the same. We refer to as that's equilibrium in short, or C, it is the equilibrium constant from the concentration terms. So let's look at the equilibrium reaction here. Let me just draw the arrow again. This time I'll draw the arrows both ways, on above and below, just to illustrate this. So this is a reaction at equilibrium. So what is the equilibrium expression for this one? Equilibrium constant expression. So we can write K will be equal to, that is equilibrium constant, concentration of the product raised to the coefficient. Remember that, sorry, let me just go back on that one. Okay, so NO2 is the product, that's coefficient 4, and water is the second product, and that is the coefficient, which is 6. So the reactants raised to their various coefficients. So that is the equilibrium constant relationship. So those are the definitions of the term. And now let's look at another reaction. This reaction is a very famous reaction because it was used after World War I believe, by discovered by a German chemist or scientist, and that is called the Haber process, where ammonia is formed, or ammonia is made. Ammonia is a very important compound, because this was widely used in the use of explosives during those era. So the two reactants are nitrogen gas and hydrogen gas. Now again, this I should write it with the arrows. So that should be the forward arrow, and I should write also the reverse arrow. Yeah, I'm not putting in the right arrows here in the reaction because of the formatting in my computer. So just note that in the chemical equation we are showing the double arrow to indicate equilibrium. So we represent the equilibrium constant based on the concentration of each of this will be concentration of the product, that's ammonia, raised to its coefficient, which is 2, and concentration of the reactant. So this one is nitrogen, coefficient 1, and hydrogen, coefficient 2. Sorry. So that should be a correction in here, should be changed to 3. Let me cross this out. It should be 3. So that's a mistake in that one. So that's the equilibrium constant expression for the reaction. So now if you have the following scenario, so if you have equilibrium concentrations, I'd like you to note this one is actually stating that you are given the concentration. If you have the following equilibrium concentrations in a Haber process, notice that you have ammonia 3.1 times 10 to the minus 2 moles per liter, nitrogen 8.5 times 10 to the power minus 1 moles per liter, and like hydrogen 3.1 times 10 to the power of minus 3 moles per liter. So you can apply this and calculate the value of K. What is K, right? So in the next slide, we'll see that. So calculate the value of K at 127. Now, I like to highlight this. Equilibrium constant. Equilibrium constant, K, is constant at a specific temperature. If we change the temperature, then the value of K is going to change. But if at the same temperature, it doesn't matter what positions of equilibrium. Notice that I'm using the word positions. It doesn't matter what position of equilibrium, you will still have the same value of K. Okay, so here, question is calculate the value of K, the value of the equilibrium constant K at 127, and then calculate the value of the equilibrium constant at the same temperature. Notice that at the same temperature for this reaction. And I'll come to this reaction here a little bit more later on. Let's just look at this one here, the first one. So calculate the value of the equilibrium constant at 127 degrees Celsius for the following reaction. If you look at this reaction here, let me draw the arrows. Notice that I'm trying to avoid this weird sign here because it'll just crowd up my arrows. Otherwise, I'll put the two arrows very close to each other. So here, notice now that ammonia is changing or breaking up to form nitrogen and hydrogen. If you look back at this equation here, Let me draw this again. If you look back at this equation here, you will see that this is the written in the forward. Okay, forward. So this is in the forward direction, and that is the equilibrium constant for the forward direction. So let's go to this next one here. If you look at this reaction, this is the reverse. Let me just say, it was the reverse of the reaction we looked at previously. So this is the reverse reaction. Okay. So keep a note on the forward and the reverse process. Same reaction, same temperature. And now let's look at this third scenario here. Now instead of the reverse, this one is still forward. Notice from what we had previously. Instead of reverse, this one actually has reduced these quantities or the coefficients by half. So 1/2 of nitrogen, 3/2 of hydrogen, combining to give you 1 of ammonia. So if you look back at the previous equation, I'm not going to do that, you will see that you're basically dividing the entire equation by 2. So this involves dividing the previous equation by 2. Okay, let's look at this as we go. So the balanced equation, this is the equation, which is the primary equation. Okay, let me draw the arrows. Okay, so nitrogen reacting with hydrogen, 3 moles of hydrogen to give you 2 moles of ammonia. So the K value will be written in this form: ammonia, concentration of ammonia squared divided by concentration of nitrogen to the 1 and hydrogen to the 3. So substituting the values, because we are given the concentration values in the question that we previously looked at. So here are the concentrations. And mind you, these are the equilibrium concentrations, so we substitute that in. So plug the numbers in and then evaluate, you get the number. Notice that in equilibrium, generally no unit. Okay, let's continue. The equilibrium definition, or the equilibrium constant for this example that we're looking at, is this value here, 3.8 times 10 to the power of 4, which is the ratio of the concentration of products raised to the coefficient over the concentration of the reactants raised to the coefficient and the product of that. So notice that no unit in terms of the value of the equilibrium constant. Now, if we look at the reverse reaction, that's our next consideration. this leads to something different. So when you reverse the reaction, notice that the product is what the reactants were before. So this time the product is nitrogen and hydrogen, and the reactant is ammonia. So when we do that, the value of K, notice that, is essentially the reciprocal of the forward equilibrium constant. So K prime is this term, which is the products over reactants. It'll be the ratio 1 over K, and that is 1 over 3.8 times 10 to the power 4, and that gives us the value. So in other words, what we're saying is that the forward reaction is a big positive number, which is this K here. The reverse reaction is a very small number. So what does that say about this reaction? What we can say is this: the forward reaction let me try and write this. Forward is very much favored. Okay, it's favored. I have to get used to this screenwriting. So forward is very much favored, whereas the reverse is less favored. So we'll look at that in terms of the value of their K's. That's the K value for the forward, which is a huge number, and the K value for the reverse is a extremely small number. So that means the forward reaction is a favored reaction. Now let's go to the next one. In the third part of this question is, what is the equilibrium constant when you reduce the coefficients by half? In other words, you divide the entire equation by half. Essentially, what happens is that the coefficients are going to be reduced by half, and therefore you will get this expression here. And how does this expression compare with the first one? Notice that if you reduce the coefficients by half, you basically, this is the value K. Notice that this is the K of the forward reaction, products over the reactants. You are basically raising the exponent of K to the half. So let's see, there you go. So if you are going to multiply an equation by a factor, in our case here we will multiply it by half, so that is going to raise the K value to the exponent of that factor you're multiplying with. So it can be either multiplying by half or multiplying by 2 or any constant, any integer. You will be able to apply it in this form. K double prime is going to be K raised to the power of the coefficient or the factor that you are multiplying the equilibrium with. So that will be the value of the equilibrium constant. For the multiplying the equation by half, it will be 3.8 times 10 to the power of 4 to the half, and that will give us the value. Again, let me emphasize, no unit for the equilibrium constant. So now let's look at the generalized expression. If you have the chemical equation here, it's the with the forward and the reverse. you will see that that is the equilibrium constant expression, products to their coefficient, the raised to the coefficient divided by the reaction to their coefficient. And reversing the reaction, you will notice that it will be the reciprocal of K. So if you reverse the reaction, that means this will be the numerator and that will be the denominator, as you see here. It'll be reciprocal of K. Now if you multiply an equation by a factor, let me again put this here. If you're multiplying an equation by a factor, for example here, if you're multiplying it by this factor n term, so the equilibrium constant value will be K raised to the power of n. K raised to the power of n. So there is another relationship that I will describe maybe a little bit more later. Okay. Now, if you notice this equilibrium constant quantities that are shown in here. So these are 3 different experiments shown in here. Notice what happens. Here, the initial concentrations. Notice that, initial concentrations. So if you start with the initial concentration of nitrogen to be 1 molar, initial concentration of hydrogen 1 molar, ammonia, which is the product in this case, 0. So equilibrium concentrations, notice the equilibrium concentration, 0.921, 0.763, 0.157. Right? These are the equilibrium concentration values. These are measured experimentally. Now, this is at the same temperatures. These 3 experiments are done on the same temperature. So let's calculate the value of K. So you plug these numbers in to this expression of K. Sorry, it's not really showing very well. This should be N2 raised to the power of 1. Let me just so this should be N concentration, that's N2, sorry, N2, and this one is H2. Raised to the power of 3. So that should be the formula for the equilibrium constant here. And you calculate the value of K in this first experiment. You get 6.02 times 10 to the power minus 2. Now let's look at experiment number 2. Here you start with 0 of the reactants, that is no amount of nitrogen, no amount of hydrogen, 0 and 0, and you start with 1 molar of ammonia. So in other words, you start with the concentration of ammonia at the start is 1 and the other 2 are 0. Again, let the system equilibrate or come to an equilibrium. Notice what happens. You'll have these concentrations which are different from the top one, but if you substitute this concentration into the K equation, you will get pretty much the same value. And that's what equilibrium constant is. If you are dealing with equilibrium constant at a constant temperature, you would expect the same K value. You do the same for experiment number 3. This time, instead of starting with just the reactants or just the products, you start with some quantities of the reactants and products. You look at this: 2 molar of the nitrogen, 1 molar of the hydrogen, 3 molar of the ammonia. So in other words, you have some quantities of all the entities in the reaction. Let it run and come to equilibrium. Notice what we get. These are the concentrations, and you work out the value of K. Lo and behold, still the same value, which is what we should expect. And what is showing in here is this: the 3 different settings here refers to the 3 different positions of equilibrium. So the 3 different positions is shown by the different concentrations of the products and reactants at equilibrium. However, the equilibrium constant is the same. So in theory, this is what we often say, that you may have multiple possible positions of equilibrium, but there is only one value of the equilibrium constant. So equilibrium position, it refers to each set of equilibrium concentrations. There can be infinite number of positions for a reaction, and it depends on the initial concentrations. Now, equilibrium constant is one constant for a particular system at a particular temperature. I'd like to emphasize that. So here is a particular temperature. It remains unchanged and depends on the ratio, and that is the formula that we've been looking at. Okay, let's look at equilibrium positions. The following results were collected for 2 experiments involving, let me just adjust my screen. Let me stop this. Okay, let me go back. So you see there's the following results were collected for 2 experiments involving the reaction at 600 Celsius between sulfur dioxide and oxygen. Notice that this is the initial concentration of SO2, initial concentration of oxygen, and initial concentration of SO3. These are the equilibrium, and that is initial, that is equilibrium. So 2 experiments, so that the equilibrium constant is the same. So what do? You find the chemical equation. Let's write the chemical equation. So this is the chemical equation. Again, let me write the arrows here. Okay. So 2 moles of sulfur dioxide and a mole of oxygen combine to give you 2 moles of sulfur trioxide. So here, K value based on that should be sulfur trioxide squared over sulfur dioxide squared, oxygen to the 1. So this follows the coefficient. Note that. So this is the equilibrium constant. Now we can substitute, and please note when we are looking at this, that this concentrations here are the equilibrium concentrations. These are the equilibrium concentrations. Notice that these are different from the initial concentrations. So when we have this, remember that it is essentially these are the equilibrium concentrations. Okay. So we're ready to substitute that in for the 2 experiments. Let's calculate. So these are the values for experiment 1, 4.36, and experiment 2, 4.32. Now you will see these 2 values are comparable. And based on the idea of accuracy, you will see that they differ in the last digit, and that is what is expected in an experimental. If you're doing an experiment, you should know this, and that is your value should be pretty much in agreement, which is precise and also accurate, and the only error that is expected will be in the last digit, and these results here are showing exactly that. So we can say that the value of K is constant. All right, let me move on to the gases, and I will finish off this segment of lecture. And that is, when we're dealing with gases, we are going to notice that now in terms of concentrations, we have to consider pressure, because, you know, in gases, we normally handle them with the variable pressure. So let's just bring in some of the background knowledge of gases we have. We know the ideal gas equation. Pressure is equal to, PV is equal to nRT. And if we rearrange this equation, pressure will be N over V. And notice that N over V, this is moles over volume, is concentration. So that's the concentration term. So what we can do, that instead of substituting concentration, we can substitute in the ideal gas term. So we know that in equilibrium constant, this is concentration. That's what we call Kc. Remember, I told you this is Kc because it is dealing with the concentration. So it's dealing with concentration. And now we can write the equilibrium in terms of pressure. We say partial pressure because that's the pressure of the individual entities or gases that are contributing into the system. So here will be the pressure of the products raised to the power of 2, which is exactly the same we do in concentration, and the pressure of the reactants raised to their coefficient. So we call this one Kp. Kp and Kc are unique. They are two different constants. This one is based on moles per liter quantity. This one is based on pressure. What pressure units? You can use atmosphere in pressure unit. And since it's a ratio, really, it doesn't really matter that much. But we will look at that in a broader context here. So in these equations, K and Kc are commonly used symbols for equilibrium constant in terms of concentrations. Okay, that's in concentrations. There's two, K and Kc, whereas Kp is used for pressure. So when you're dealing with pressure units, you can calculate the Kp. So let's consider this relationship. Now let me just change this again to the, okay, so we have this forward and reverse arrow for this reaction. Notice the states. This one is a gas, chlorine is a gas, and NOCl is also a gas. So these are all gas quantities. So if you're given the pressure at equilibrium, notice that they're all given in atmosphere unit. So you should be good to carry this substitution directly. So again, what we will do is write the equilibrium constant K, which is now going to be Kp, and using these pressures, we can find the value of Kp. So again, at any temperature, this K should be constant. So in other words, if it's 25, then K value will be constant at 25. So substituting in the pressure that is given, so this one will be 1.2 squared over, sorry, this squared here should be shown outside of the parenthesis, just a minor typo there. instead of inside the parentheses. And likewise, that's okay. So you get this. All right, let's evaluate this. And it comes to 1.9 times 10 to the power of 3. So that's the Kp value. All right. So question is, what's the relationship between Kc and Kp? So if you have an equation as such given here, so again, I really apologize for this mess in this equilibrium error. Let's come to this. So again, using this equation, a plus b giving you c and d with their coefficients, you can write the Kc and Kp expression as such. Kp is equal to K, which is, this one is Kc, right? So if I write Kc there, Kp is equal to Kc multiplied by the gas constant temperature term raised to the delta n. Now, what is this delta n? This delta n is the sum of the coefficient of the gaseous products minus the sum of the coefficient of the gaseous reactants. Okay. You have to look at the chemical equation, like what is shown, and look at their states. You know, what's the state? For example, if it's a liquid, if it's a gas, okay, if it's a gas, I'm just saying, and if it's a solid, this one is a solid. If you're looking at the state, so what we're saying in here, the sum of the coefficients of the gases products minus that of the reactants. So in other words, this is the only gas here. If this is liquid and this is solid, this is the only gas here. So it'll be L, this is the coefficient L, minus J, because this is gas. You are not going to take care of this two because they are not gas. Only the gas species that are there in the chemical equation. All right, let's look at. So using Kp, obtained in an example that we looked at previously, calculate the value of K, which is Kc, at 25 degrees Celsius for the reaction. So we have the same reaction here, and we're going to work out the value of Kc. Right, so this is the relationship. Kp is equal to Kc RT delta N. Let's work out the temperature, and let's work out the delta N. Now, what is the delta N? 2 minus 2 plus 1. Sum of the coefficients of the product, which is in the gas state, it must be the gas, and sum of the coefficient of the reactants in the gas form as well. Okay, so that is 2 minus 2 plus 1, that will give you minus 1. Now let me go back to the reactants here. So the product is this 2 minus, this is gas and gas, that is gas. So 2 minus 2 plus 1. That's what we got here. That's what we get here. That's where these numbers are from. 2, that's a product, minus 2 plus 1, these are the coefficient of the two gases in the reactants. So delta N basically work with a coefficient. And so therefore you substitute that in. That is equal to same expression. If it's to the negative 1, that'll be over the ratio of RT, and substitute in the numbers. So K is equal to Kp. Now I've rearranged the equation to RT. So it'll be 1.9 times 10 to the power of minus positive 3 times the gas constant. Notice that we're working in atmosphere, so this is the gas constant, that's temperature in Kelvin, and you get this value. So that's a Kc. Notice the difference. This is Kc, 4.6 times 10 to the power of 4. Compare that to Kp. Kp is this value here. So that's Kp, and this is Kc. Notice the difference of the two. So I hope that highlights the importance of the significance of the gas and the solution concentrations as we consider them. Okay, this is the end of the first video on this class on the topic of equilibrium.